of the important concept in this Nobel Prize Award research. Okay, so yesterday it was awarded that the Nobel Prize in Physics of 2022 goes to these three gentlemen for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Do you understand what he's talking about? Maybe it looks like you don't understand, but at least, yes, you know entangled photon. And there's only one more step to understand the rest. What is the meaning of the violation of Bell inequalities? Okay, so today I want to talk about this, and you will find that you already know a lot of things that enable you to understand the basics. Let's review what we did for entanglement before, right? And here I am very good in advertisement. Now I put the QR code. You will go to the video that we learned about entanglement earlier, right? If you forgot about it. We say that, for example, here, can anyone explain to me what is this? This is how many qubits? 2 qubits, right? Because we see that it is written in this way, and it has 4 basis states. In this particular case, I have one state, which is a linear combination of these 4 basis states. And I tell you that this one, we can factorize it so that it becomes a tensor product of the states in each of the subspace, the space of the electron 1 and the space of electron 2, right? And now you understand what is a tensor product. It's just like a multiplication. But basically, this system, which has 2 electrons, can be described individually by the properties of this individual space, which then go through the tensor product. That is okay, right? We also talk about entangled states. For example, this one is one of the entangled states we learned before, one of the so-called Bell states, right? This is the psi minus. Here it has the linear combination of 2 of the basis states in the 2 qubit space, 0, 1 and 1, 0. Because of this, no matter how you do it, and no matter how you transform the basis or coordinate, you cannot factorize it into 2 subspace tensor product, a simple product of 2 subspace states. Okay? And this is called entangled state. We have learned this before. Any questions? What is the problem of, not a problem, what is the properties of entanglement? For example, it can lead to so-called EPR paradox, right? We have details here, you can review again. The Einstein, Podolsky, and Rosen paradox. What is that? Suppose I have 2 electrons. I prepare them in an entangled state. This is the Bell state, right? Compared to my previous slides, I was showing another entangled state, which is 0, 0 plus 1, 1. Here I show 0, 1 minus 1, 0. Doesn't matter. It's still an entangled state. I then carefully separate them to very far away, 100 light years away. Basically, you cannot communicate within 100 years according to special relativity, right? I do it carefully so they are still entangled, means the whole system which composed of these 2 electrons are still entangled and described by this wave function. Then I decided to do a measurement on the first electron. I measure in the 0, 1 basis. Right? Or in our language, maybe the magnetic field is pointing in the z direction. I measure the energy. When you do the measurement, the wave function collapses. Because this is in a superposition, it may collapse to 0 or 1. We have 50% of getting 0, right? Assume that we get 0 for electron 1. Then the whole wave function will collapse to 0, 1. I have some typo I forgot to change. First of all, this should have the bracket, and this is 0, 1 instead of 0, 0. should be 0, 1, because my example last time was 0, 0. It will collapse to 0, 1, right? Why? Because the whole system is a linear combination of 0, 1, and 1, 0. If my first electron collapses to 0, then the whole system's wave function must collapse to 0, 1. I cannot collapse to 0, 0 because I don't have the 0, 0 component, right? And because of this, what will be the value of the electron 100 light years away? It will be 1, right? And that is why the system now is at 0, 1. That's no problem, right? Of course, we talk of the spooky action at a distance, but we say that doesn't violate special relativity. We don't worry about that. But we do have the so-called EPR paradox. What paradox is this? If I get 0 here, I can tell my friend who is 100 light years away, although it takes many hundreds of years to tell my friend, but I can tell my friend that I have 0, so my friend knows that I also know that the electron 2 must be at one state, right? It must be at one state. So I'm 100% certain this is at one state without measuring it. My friend did not touch the electron, but we already know that it is in one state. But then my friend decided to measure in the plus-minus basis corresponding to have the magnetic field in the x direction. Then it will collapse to either plus or minus, right? So as a result, for example, let's say it collapsed to plus. Then it also means that my friend is 100% certain the electron is in the plus state. Right? For these details, you can also take a look in the old video. Right? If you forgot why, we can have plus. Because 1 is a linear combination of plus and minus. Right? 1 equal to 1 over square root 2, 0, plus 1. Right? So what does it mean? I'm 100% certain it is in 1. At the same time, we are also 100% certain it's in plus. That violates the Heisenberg uncertainty principle. That is the so-called EPR paradox. We only stopped here last time in our class, right? And I thought that we are not going to talk about Bell inequality. But because of the Nobel Prize, we should continue because you will see that you are so close to it. Now, how do I explain this paradox? To explain this, why it violates the Heisenberg uncertainty principle, we can say, well, there's something called long locality. Maybe the measurement of electron 1 affects the measurement of electron 2. Somehow when I measure electron 1, it sends a signal to electron 2 right away due to some physics. And it needs to be faster than the speed of light. It does it instantaneously, which then prevents I don't know what's going on, but you can see it now. Okay. It then prevents electron 2 from being measured in plus-minus spaces. Okay, it has some mechanism, then the measurement becomes invalid. This is possible, right? So this is one explanation. But this will violate special relativity because you need to transmit signal faster than the speed of light, right? So we choose not to believe in this, but who knows, in the future, maybe someone came up with a better theorem. But at this moment, we feel this is really spooky, okay? Long locality is what you usually see when we talk about this Bell's inequality or whatever. They want to say everything interact with each other locally, right adjacent to it. So it means you need to propagate the signal throughout the space slowly, okay? Another possibility is to say quantum mechanics is incomplete. So while we are talking about all these states, it's not a complete description. It is incomplete. There are some hidden variables to describe the state. But we just still don't know them yet. We are not smart enough. We still don't have the theory to describe it yet, but maybe there's some hidden variable. And that's why you have this paradox. What does it mean? It means that when you generate this electron hole pair, it already has something imprinted, people call it DNA, imprinted in these two electrons. They have an extra variable telling it that if this electron is up, the another electron must be down. For example, we will say the electrons are actually not in superposition, right? That's what Einstein preferred. Like when I don't look at the moon is still there. This is called realism. Whether the state of the object is independent of my measurement. Now you say it's in superposition. I claim that it's just because you don't know it well. It is not. It has some hidden variable. It's not because I look at it, then it collapses to 0 or 1. That is one thing. And also it can be fully described by the hidden variable. For example, electron 1 can be in one of these states. Look at this. Instead of at 0 and 1, or superposition of 0 and 1, electron 1 is definitely in 0 plus a hidden variable, which is plus, or 0 plus a hidden variable, which is minus. Okay, it's in one of these states. This is a 1 qubit state. I'm not talking about 2 qubit. One has 0 and one has plus. I just say that this electron, while we see is 0, actually is 0 plus 1, a hidden variable plus there, right? But our quantum mechanics just not good enough to describe it. We are not able to find out the hidden variable yet. Similarly, the electron 2 can be in these four states. Right? So for example, when I prepare electron in 0 and 1, then they are in this blue group. Then you might have a first electron at 0 plus, second electron at 1 minus. Then you just let them go to two different places. Then when I measure the electron, I get 0, then the other one must be 1. And also, or maybe it was prepared at the green pair. When I got electron 1 equals to 1, then the other one must be 0 because it's predetermined, just like a graph. I have blue and yellow, I put them together. If you get yellow, I must get blue. You get blue, I must get yellow. And in addition to that, I also have some hidden variable. And you see that I have 50% of the chance to get plus or minus if I measure in the plus minus basis. This is not the quantum mechanics we have been learning, so don't feel confused. Try to map to what you are learning, okay? So this is the summary. If both measure in 0, 1 basis, right? The one on Earth, the one on 100 light years away, you will always get opposite. You get 0, electron 2 get 1. If electron 1 measure to be 1, electron 2 will be measured to be 0. But if people choose to measure in plus minus basis for electron 2, no matter in which cases, I have 50% of chance to get plus or minus. This kind of explains the EPR paradox result, if we assume there is hidden variable. Okay? Yeah. You can, I think you can construct even with more electron. I'm not into this, but I think you can still use this one to keep proving that you can you can explain the EPR paradox with more and more hidden variable. Okay? But however, what happened to this Nobel Prize or this Bell's inequality? Basically, it is that the Bell's theorem says that quantum mechanics is incompatible with the local hidden variable theorem. Just now, I used local hidden variable to explain the EPR paradox. But however, you cannot explain everything in quantum mechanics. And one of them is the so-called the violation of Bell inequality. So we are going to show that there's something called Bell inequality. this inequality is correct if you have the local hidden variable theorem, like what we are talking about. You will get this inequality. But we will show that in quantum mechanics, you actually is going to violate the Bell inequality. Okay? Now, that is the theorem, right? In theory, I'm going to show you that indeed it violates because we have the theory. But you need to prove it experimentally. And that is what this Nobel Prize is about. They have conducted different types of experiments to show that the Bell inequality is violated. And thus, Bell's theorem is correct. And thus, local hidden variable theorem or this low hidden variable explanation is wrong, incomplete. So basically, it brings us back. We still don't know why we have this EPR paradox. We only show that this is wrong. Then maybe you can transmit signal faster than the speed of light, or you need to further discuss philosophically or come up with a new theory. Okay? So in summary, that is what about the Bell's theorem. And the Nobel Prize is about they did the experimental work to prove that Bell's theorem is correct. And Bell's theorem says that the Bell's inequality is violated in quantum mechanics. Okay, so this is a summary. I hope that you can relate to it. And actually, I said something wrong in my previous lecture because I did not prepare. I keep saying that the Bell's inequality is maintained. Its opposite is violated. Okay, if you watch that video. Okay, but we have learned enough basic stuff that enable us to really look into this theorem. Use some example. People usually use the photonics qubit as an example to explain the Bell inequality. There are many different types of Bell inequality, but we just take one example, one concrete example. And I find this Wikipedia's example is easier to understand for us because it's shorter, but maybe not easier to understand, but mathematically it is easier to do the calculation and from the cases. Okay, so we'll look at this. Now, let's say for that 2 electrons, right? We can either measure the electron 1 in 0 or 1 basis. I call it A0 measurement, okay? This measurement called A0. It just means that I put the magnetic field in the Z direction, right? And then I measure the energy. Then I know that whether spin up or spin down. That is 0 and 1. I can also measure in the plus-minus basis corresponding to the putting magnetic field in the X direction. I call it A1 measurement. This is going to give me plus or minus. Again, spin left, spin right, same eigenenergy. Is this okay? The first electron on the Earth. I can perform either A0 or A1 measurement. I can set up the magnetic field up or horizontally and measure how it collapses, measure the energy of the electron spin in the magnetic field. Okay? Now, for B, which is far away, it can also choose to measure at B0 and B1. But look at this. B0 and B1 are not the same as A0 and A1. Just in order to prove it, demonstrate this theory, B0 is said to be X plus Z divided by square root 2, so negative. So it's in this 45 degree in this direction. This is a 2D plane. And then B1 is said to be X minus Z, so it is here in this direction, right? Then of course, this is 90 degree, and this is also 90 degree, and this is 45 degree, right? Nothing special, it's just saying that, my friend, 100 light years away, just rotate their magnetic field in that direction when they perform the measurement. And then they will get spin, I don't know what to say, spin up and down, but not really up and down, but along this axis, right? Spin here or spin other axis. Is that okay? So then we are going to do a lot of measurement. you're going to get the result A0, small a0, small a1, small ab, small b0, small b1. And when you measure, you could get either 1 or 0, right? Because this is eigenvalue, right? You will get either 1 or 0. Now, if I do a lot of measurement, and I randomly select the orientation. But for example, I don't talk to my friend because we're far away. I just use dice. I randomly say, oh, this time I want to do A0, right? Then I may get A0. And then my friend may happen to do B0 direction, right? And next time maybe I want to do A1, but my friend is doing B1. Randomly, right? You don't know which one we choose, right? We only have 4 possible combinations. A0, B0, A0, B1, A1, B0, A1, B1, right? And then you just find out the value you measure. You will get either 1 or -1 in each of these terms. And I decided to come up with an expression. This is just a make-up expression. I want to find the average value of this expression, okay? Just an expression I want to calculate. It doesn't have any physical meaning. I just say that, okay, I want to average all the measurement that we get. Based on this, you see, this one I can factorize. If the best case, you only have a few possible results for each of these 4 combinations. Let's say I have 100 measurements. Then I have 25 of this combination because I would just put 4 of them together. And because I do it with a lot of measuring randomly, on average, I should have 25 of this combination. Then A0 plus A1, it can be either they are the same, then this becomes 2, right? And A0 minus A1, if they are the same, then this one becomes 0. And this can be either 1 or -1. So no matter what, you always see that the result is either -2 or 2 when you just put them together. Then what is the average value of negative of 2? Or 2 or -2, right? You either have 2 or -2 and you do a bunch of measurement. It must be less than 2, right? Because you may have 2 minus 2 minus 2 minus 2 plus 2. But on average, it needs to be less than or equal to 2. So basically, this is that this one is a result of hidden variable. You will get this if you use hidden variable theorem. You naturally will say, I do all this measurement, I naturally will get, on average, less than 2 for this expression. Again, this expression has no special physical meaning. Just superficially, you don't see any physical meaning. We construct this to show the Bell's inequality. And this is the so-called Bell's inequality in this case. Okay, so with hidden variable, the average value of this must be less or equal to 0. And now, from quantum mechanics, we will be able to prove that now the electron will try to make in an entangled pair. We decided to do that. And then we can show that this average value is 2 times square root 2, which is larger than 2. So as a result, Bell's inequality is wrong. And thus, hidden variable explanation is wrong. This is theory. But what they did is they experimentally proved that not this one, but the photonics one, or many other different experiments, they proved that Bell's inequality is violated. And that's why you cannot explain quantum mechanics by saying that there has hidden variable inside quantum mechanics. Although we still don't know why, but it's not because there's hidden variable. Is that okay? So I hope to bring this to you, but this is a good exercise for us to practice our math, right? So I would like to show how to calculate this one from now on, right? So let's do some practice. First of all, we said that A0 measurement is in the z direction. What is the operator? Corresponding operator. Magnetic field in the Z, huh? Sigma Z, very good. Sigma Z equals to 1, 0, 0, negative 1. And again, we discussed all these Pauli matrix, right, in this link already. How about A1? It's in the X direction. Sigma X, very good. Which is 0, 1, 1, 0, right? Now, what is the matrix for B0 then? Do you remember how to find it? This becomes finding the operator of the spin matrix, right? The spin matrix in a direction corresponding to the real 3D space direction here, right? Do you remember how to find that, the equation? Do you remember the equation? This one. Does it ring the bell? N is the unit vector in the 3D space, signify the direction of the magnetic field. And sigma is the vector or the Pauli vector. Remember that? Basically, if I look at this one, this direction, what is the direction in the real 3D space? It is 1 over 1 over square root 2 for x, 0 for y, 1 over square root 2 for z, right? That is the unit vector in this direction. Actually, I make a mistake. It needs to be negative. Do you agree this is the negative x minus z unit vector? This is xz, right? This is x, right? So this is negative x, this is negative c. So this is negative x plus negative c. Make sense? And what is the sigma vector? Do you remember? Sigma x, sigma y, sigma z. Okay, so you do the dot product, what you get is 1 over square root 2 negative sigma x plus sigma z. So we learned this before. I think we did that in assignment 1. You should be able to construct the matrix easily. But if you forgot, fair enough, it's not simple. But you know that you know how to do it already, right? How about B1? B1, I'm not going to go through the derivation, but you can find that it is just sigma x minus sigma z divided by square root 2. But let's put this into the matrix. What is this matrix? What is sigma x plus sigma z? What is sigma x plus sigma z? Yeah, just A0 plus A1, right? Sigma, what is that? 1, 1, 1, negative 1, right? You just add these two together. How about this one? What is sigma x minus sigma z? Sigma x minus 1, because 0 minus 1, yeah? And then 1, 1, 1. Is that okay? Say again? 1 negative 1 over root 2. This is, that's right, yeah. Because B1 is in this direction, is x minus z, right? Okay. So we can construct the matrix, right? So after constructing the matrix, then we want to understand, okay. how to do the calculation. So my goal, right? My goal is to calculate this. What is the meaning of this then? A0 tensor product B0, right? What is the meaning of this? A0 is the operator tensor product B0 because we have two electrons. A0 is for the first electron, B0 is for the second electron. And you do the tensor product, it becomes the operator for the two-qubit system. Okay? But what is the meaning of this bracket? It's just a simplification. It means we put, what do? We put psi minus to it. And then now I'm not going to write down the tensor product symbol to make it simple. That's what it means. Do you remember in assignment 1, I asked you to find the FH value of the sigma X or sigma Z, remember? Of a given state, right? The FH value, the FH measurement value is just the operator sandwich by the bra and cat of the state. That signifies what is the FH value I will measure under this operator. So the first thing I need to do is find out what is A0 tensor product B0. This is not difficult. How do you do it? A0 is 1, 0, 0, negative 1 from the last page. Tensor product B0. B0 is a little bit more complicated, but we calculated it already. It is negative 1 over square root 2, 1, 1, 1, negative 1. Right? I just show you. This is the B0, 1 over square root 2, 1, 1, negative 1, and A0 is just 1, 0, negative 1. How do you find the tensor product of two operators? Yeah, 1 times 1, 1, 1 minus 1, 0 times 1, 1, 1 minus 1, 0 times 1, 1, 1 minus 1, 1 times negative 1 times 1, 1, 1 minus 1, right? So the whole thing, I'm running out of space. I will just write it as negative 1 over square root 2, 1, 1, 1, negative 1, 0, 0, 0, 0, 0, 0, 0, 0, negative 1, negative 1, negative 1, and then 1. Here I have a typo. This one is negative 1. Is this okay? Yeah, that's how you do the tensor product. Now with this, then I just do a regular multiplication, but before that I can just do the exercise a little bit more, remind ourselves. How do you write the psi in a column form? Psi minus in column form. But maybe you forgot what is psi, right? The psi I gave you is 1 over square root 2, 0, 1 minus 1, 0. How do you write in column form? What is that? Okay, do not forget this 1 over square root 2 is 0, 1 minus 1, 0. Why? Because again, this signifies how much 0, 0 you have, how much 0, 1 you have, how much 1, 0 you have, how much 1, 1 you have for this state. Okay? So how about the broad version of psi minus? What do you do? Becomes a row vector, right? And I don't need to take the complex conjugates because this has all real coefficients. Right? So the FH is easy. It's just A0 tensor product B0 FH on this state, right, is psi. So it is 1 over square root 2, 0, 1, negative 1, 0. Then you multiply the whole thing, negative 1 over 2, the whole matrix 1, 1, 0, 0, 1, negative 1, 0, 0, 0, 0, negative 1, negative 1, 0, 0, negative 1, 1 times 1 over square root 2, very long, 0, 1, 0, 1, 0. Right? So what I'm doing is this. This one equals to this one, right? Because we're calculating the FH value of this given state when measured by this operator, right? So that's why the broad version I put here. So here I have a typo. This one should not be this. This is the broad version of this one. And I put A0, tensor product B0, which is here. And then I put the psi minus the cat version. And then I just do matrix multiplication. And you will see that this equals to 1 over square root 2. Any questions?
Can you explain the top line?
Which top line? This line? Yeah. This line, this is just an abbreviation. It means what is the FH value of this operator, which is meaningless because you need to say the FH value for a given state. And the reason I dare try to write this because we assume that the given state is this state already. Okay? So this line is just, I spell it out. I say it is the FH value of psi minus. So we would bracket psi minus on the operator. Yeah, because I want to find the FH value you will measure for this psi minus state. Okay? If you forgot, let me remind you again, right? What is the FH value you will get for the one state when you do sigma C measurement? Okay? For example, so if my state is at 1, what is the FH value you will measure? When you do a measurement at state 1, what do you get? There is a state. Its state is at 1. When you do measurement, what would you be? What will you be? Huh? The state is at state 1. When you do measurement, what will you be? I asked the girl, do you like me? She said no. And I keep asking, what do I get? No, right? So it is at state 1. I keep measuring. What do you get? 1. Correct? If you have a linear combination of 0 plus 1, you do measurement, it can collapse to either 0 or 1. Now it is at 1. You do the measurement, it collapses to 1 forever. Right? So what value is it? What's the eigenvalue when the state is 1? What's the eigenvalue when the state is 0? Not eigenvalue, I mean the corresponding eigenvalue. Yeah, plus 1 for 0, right? So it should be minus 1, right? When I keep measuring 1. Right? So how can I find it? If I do this. This must be negative 1. Because no matter how many times you measure, I must get negative 1. This is the FH value I will get. But in general, you might not have 1, right? You have alpha, beta, right? And this is easy to prove because 1 is 0, 1. Sigma C is 1, 0, 0, negative 1. And this is 1. This is 0, 1 because it is 1. Right? So what do you get? You do the multiplication, you get 0, negative 1. And then you do one more multiplication, you get 1, right? Negative 1, right? Just to show that a special case, yeah, this one gives me the FH value. But if you have alpha, beta, it's not 0, 1, then you will get the alpha, beta. That is what we had in the assignment, isn't it? Alpha squared plus beta minus beta squared. Do you do it yourself? Yeah. Remember? Remember I asked you what is the FH value you will get in sigma C, and I asked you to think from the classical point, probabilistic point, and then use the equation. right? So this one is the average value you will get for this operator for a given state. That's why I write in this way. Okay? Now, then I will not do the rest. You need to do at the other computation yourself. Maybe we can put it in the midterm. Right? And then you will find that A0 tensor product B plus A0 tensor product B1 plus A1 tensor product B0 minus A1 tensor product B, what is that? B1, right? This is equals to 2 square root 2, which is larger than 2. So here I show you that in quantum mechanics, you are allowed to prepare an entangled pair. And then you find that the probability, the average value of this expression is 2 square root 2, which is larger than the 2 given the boundary, given that the Bell inequality based on hidden variable. That's why the hidden variable theorem is wrong, cannot explain. Right? The theory showed that. That's okay, but if the theory is wrong, of course you get wrong stuff, right? But they did the experiment. They showed that indeed Bell's inequality is violated. And thus, we cannot explain quantum mechanics in the using hidden variable. Yes.